So my talk would be about the instrument which made this discovery. So this instrument is called Advanced LIGO, and LIGO stands for Laser Interferometer Gravitational Wave Observatory. So just to remind you, gravitational waves, as Ajit told you, are freely propagating oscillations of the gravitational field, and physically gravity manifests itself as a tidal effect. So you can say that gravitational waves are oscillating tidal gravitational fields which propagate out from the source. So if you ask for the properties of gravitational waves in general relativity, one can show that this tidal force field looks like either a plus or a cross, and therefore if a gravitational wave is incident normally on a ring of particles, it will be tidally stretched and squeezed in an oscillatory time dependent manner. So if you want to detect gravitational waves, you really have to measure this amount of squeeze, and to quantify it, you introduce a notion called a gravity wave strain. If you take two test particles and separate it by a distance L, if a gravity wave signal squeezes it by a separation delta L, you take the ratio of delta L by L. As Ajit mentioned, gravitational waves were predicted by Einstein in 1916 as an important consequence of general relativity. He gave what is called as the quadrupole formula, using which one can estimate that if you have a lab source, the strain it produces is of the order of 10 raised to minus 39. It is very, very feeble. And that's the reason Einstein himself realized that this has practically a vanishing value in all conceivable situations. Ripples would be vanishingly small and nearly impossible to detect. However, by 1957, in an important conference which is called the Chapel Hill Conference, by the work of people like Felix Pirani and Hermann Bondi, the fact that gravitational waves are physical, this issue was resolved, and in a sense the quest for gravitational wave detection was really born. Because Pirani pointed out that the tidal effect of gravitational waves are unambiguous. Mathematically they can be calculated by using the geodesic deviation equation, and this led Weber to build his first generation of detectors, which are called bar detectors. However, to get to the present generation of detectors, it was almost 50 years, and in between we had access to new technology, new sources, new understanding of sources, new computing resources, and essentially 3 generations of physicists who worked on this particular problem. So if you had a binary neutron star system instead of a lab source, then if you put such a system in the nearest cluster of galaxies, which is like the Virgo cluster of galaxies, you have a strain which is more reasonable, a strain of the order of 10 raised to minus 21. So if you can build an interferometer which is of an order of a kilometer, you have to measure a displacement which is 10 raised to minus 18 meter. So if you really want to detect gravitational waves, you really should be able to measure a very small strain and the associated displacement. Remember, this displacement is 1000 times smaller than the size of a nucleus. If you build a bigger detector, then the displacement is larger, so that is the reason we build large interferometers. And if you compare with the technology required, the Michelson-Morley experiment of special relativity essentially measures a displacement of only 10 raised to minus 9 meters. So you really needed to improve technology by 10 orders of magnitude. The story of LIGO essentially begins with 3 important documents, one of which is called the RLE paper of Ray Weiss, who basically talked about the feasibility of using laser interferometers to detect gravitational waves, and more importantly, he tried to understand all the other noise sources which we should fight against. Then there was another document which is called as the Blue Book by the community, and finally in 1989, the first proposal for LIGO construction was really made. These are the people in some sense who were behind this endeavor, and I basically show this picture to show you that when they began, they were young people like Ajit, but by the time gravity waves are discovered, they are older like me. So it essentially involved many generations of detectors, and the other person who brought in technology was Ron Drever. The project really requires support by the funding agency, and at the funding agency there was a colleague called Richard Isaacson, who essentially made sure that this long haul project was sort of funded. The project needed to be approved. This was done by Rob Vo. And finally, Barry Barish put together the technology and the working practices of the high energy physics community and built what is called as the LIGO scientific collaboration. So what I am going to talk about is the work and the outcome of the LIGO scientific collaboration. So let me remind you of what is laser interferometry. A laser interferometer is basically an instrument, a most sensitive instrument to measure small displacement. What is shown here is what happens in an interferometer. The light gets split, goes to two mirrors and then comes back, but it is shown a little more detail here. If the two arms of the interferometer are of equal length, then the light goes to the end mirrors, comes back, and because of the fact that the length is the same, there is destructive interference, and at the output there is no light which comes out. Because of the gravitational waves, if the mirrors are moved in a tidal manner, then some light leaks out, and what you try to do is monitor the light which comes out of the photodiode. So this essentially is the basic principle by which you try to detect gravitational waves. So one can say that the mirrors are acting like test masses. The passage of gravitational waves induces differential arm length change, which is proportional to the gravity wave strain amplitude. This generates power fluctuations in the output port, which are measured by photodiodes. A simple Michelson interferometer, a few kilometers long, is what is shown here, but it is not sensitive enough to detect the small changes we want to do. So what you do is try to increase the optical path length by using a Fabry-Perot cavity and making the light bounce many times. So it essentially increases the path length by about 100. Because all the light which comes out, because you're putting the instrument at this dark port, there is all the power is coming back to the laser. The sensing which you can do of the fringe can be made more accurate if there is more power in the laser interferometer. So you do what is called as power recycling, and finally to improve the interferometer response, you do what is called as signal recycling. So at the end of the day, you can say that with the technology we have today, you can not just measure fringe width, you can measure 10 by 10 raised to minus 11th of a fringe, and that is essentially what allows us to detect gravitational waves. In a sense, you can say the interferometer is acting like a transducer which converts the gravitational wave to a photocurrent which is proportional to the strain amplitude. But the point is that you can't have this interferometer clamped to the laboratory because you want the mirrors to move. So it is a more complicated kind of interferometry involving freely falling masses. But as I told you, there are a lot other noises which the interferometer is subject to, and basically therefore you really have to understand and control all those sources of noises. So the basic message is the response of the interferometer to the displacement depends on the frequency in which you are operating the interferometer, and the masses should be made free from all kinds of environmental disturbances if you want to build a sensitive interferometer. And this essentially was done by the LIGO project, and because we are trying to measure something very feeble, you won't believe it if you see the signal only in one particular interferometer. So the LIGO project essentially consists of two facilities, one at Hanford and one at Livingston. To be even more serious, even in the Hanford beam tube, you actually put in two laser interferometers. This is important because it is one of these interferometers which will come to India to create LIGO India. So what you really are trying to do is making sure that if you see an astrophysical signal only in one of them, you would not believe it. You would like to see the signal also in the other interferometer, and because you want to do that, you essentially align these two interferometers so that you can definitely see the signals if it's an astrophysical one. So this is the Hanford interferometer, 4 kilometers long, the Livingston interferometer, which is again a clone of that same one, and finally in Europe also there is a large scale interferometer which is called Virgo, which is about 3 kilometers long. These are the people who essentially brought this particular project into being in Europe. Now what are the keys which allowed us to go to the advanced instrument? So as I told you, you really need to beat a number of fundamental and technical noises that affect the measurement at this subnuclear length scales. For example, if you want to be sensitive at high frequencies, you use high laser power. If you want to be sensitive at the mid frequencies, you use, for example, lower thermal noise mirrors. And the most biggest challenge is that at lower frequencies, there is a lot of seismic noise. So you really need high quality seismic isolation systems. So the important point is that this project really involves instrumentation science at the frontiers of physics fundamental limits. This is, for example, some subsystems of it, the laser, which is really a 200 watt single frequency, single mode ND-arc laser. The challenging requirements, because you need frequency sensitivities of this particular order, amplitude sensitivity of this particular order. So you would see that in every slide which I am showing you, the requirements are at the limits of technology. This is the crown jewel, the test mass, which is made up of ultra high purity fused silica. It's a 34 centimeter diameter, 20 centimeter thick, 40 kg in weight. And if you look at its requirements, it has to be flat up to lambda by 1000. The coating uniformity should be about 0.1 nanometers. It should have absorption which is very, very small, less than 1 part in a million. Scattering again very, very challenging. So you would see again that the technologies are very, very different things, but everywhere you are at its limits. The other thing, as I told you, is you should have to isolate at the system from all the other noises. This is done by using a multi-stage pendulum system which attenuates the ground motion by 7 orders of magnitude. Even this is not sufficient, so what you really do is put this on an actively controlled seismic isolation platform which provides another 3 orders of magnitude isolation. So the important point is that today, 100 years after Einstein predicted gravitational waves, we have access to the technology to make this measurement. Again, it is a system where if there is gas inside, there will be problems, again there will be scatter. So this huge system, which is 4 kilometers long, has to be put in a vacuum system. The vacuum requirements are ultra high vacuum, etc. So you can see that on a large structure and at the level of the optics, you are really talking about technology which is only accessible today. Again, as Ajit pointed out, you have these 2 observatories. So using them, we can make sure that the disturbance we see in the detector is not because of environment. We have a lot of physical environmental monitors which include seismometers, accelerometers, microphones, magnetometers, radio receivers, weather sensors, power line monitors, cosmic ray detectors, so that you make sure that the signal which you see is not due to any one of these particular causes. Again, when you think of it as a control system, again it's a very complicated control system. So what I want to point out is that this particular experiment involves high level engineering, and essentially almost half the team in advanced LIGO really consists of engineers. So this is an opportunity not just for physicists but also for engineers. So this is the advanced LIGO instrument which made this particular discovery, and as I told you, for the first time we have an instrument which really measured displacement which is 200 of the proton radius. So it is not an exaggeration to say that this is really the most sensitive instrument on the earth, and it has come into being because there is a group of the most talented instrument builders on the planet. Therefore, starting from this detector, advanced LIGO, which made this detection in this observation run, which is called the first run. Now currently we are going through what is called the second run of these LIGO detectors, which will happen for about 6 months, and eventually by 2019 we will get to what is called as the design sensitivity, which will be about 3 times more sensitive than the detectors which we have today. Do we stop there? No, because we basically have the initial detectors which we had, which is shown here by this red thing here. But then, as I told you, in 4 or 5 years we would go to design sensitivity, but we will not stop there. We basically will try to upgrade the instruments, And with the technology which we have today, maybe we can make it more sensitive by a factor of 2. If you really want to go by for a factor of 10 improvement, you really will need to invest in R&D related to the next generation detectors, and that is where there is a scope for communities other than the gravity wave community, astronomy community, to make the contributions. For example, as I told you, it involves work in lasers, it involves work in actually building test masses in terms of coatings. So there are many other aspects completely unrelated to mechanical, the gravitational wave astronomy which is involved. So it's an invitation to the whole community to get in touch with us and participate in this exciting endeavor. What we really will do with this is the next generation science, which will allow us to study gravity in its extreme manifestation, matter in its extreme states of like neutron star matter, etc., and finally allow us to look at the cosmic history, as Professor Kip Thorne pointed out. I end by basically telling you that there are innovations in areas very different. For example, lasers, optics, metrology, vacuum technology, chemical bounding, software algorithm development, which has really happened because they have used techniques which were invented by LIGO, and these techniques have really gone beyond the gravity wave detection. And therefore, gravity wave science has really has had impact on the technology development and invention much beyond astronomy, astrophysics and basic physics. And this is what I really wanted to share with this particular audience. And this is not just a thing on paper. LIGO technology, by the standard varieties by which technology goes from fundamental physics to industry, that has really already happened. The experiment is really, as I told you, such a marvel of engineering that this experiment really received last year what is called as the Engineering Excellence Award, and it really recognizes all the achievements which this team really has achieved over the last, let's say, 20 years. So I just end by a quote by Beverly Berger, who basically said that every single technology they are touching, they are pushing, and there is a lot of different technologies they are touching. So I end by this last slide, which we basically show whenever we talk about the LIGO India project. So as I explained to you, in addition to all the basic physics, all the basic astronomy, which is all cutting edge, there is this technology interface, and therefore it's not just about fundamental science, it's about applied technology, it's about high-end computing, it's about future astronomy, and therefore I hope I have convinced you that it is an appropriate topic for this particular science congress, which is devoted to science and technology for national development. Thank you.